Hey, good evening, Red Devil Chemists. It's Coach Scott again, looking at a worksheet. This is worksheet 4G, Stoichiometry Problems. And this is a very long little worksheet because it's going to look at, well, it's not too long, it's only about 5 pages, but it's going to look at a couple of things. And there's a lot of good concepts in this worksheet that's going to help us out. So, number one, let's look at the first problem, which I feel very confident that most of you guys can do without any issues. Get my little periodic table out here. All right, so write a balanced equation for this with state symbols. Remember, that's gas, liquid, aqueous, solid for this reaction. The reaction is propane gas burns an oxygen gas, produce carbon dioxide gas and water. Okay. Water, I would say, is pretty much liquid. So, propane gas is C3H8, and it said gas. Put a G down there. Burns an oxygen gas. Remember, oxygen is diatomic. That would be gas. And it's going to produce, put a little arrow in, carbon dioxide gas and water. So, we'll call that liquid. Okay. So it asks us to calculate the number of moles of carbon dioxide gas that will be produced if 2.1 moles of propane are burned in excess of oxygen. So I'm going to use this, I'm going to do this way by dimensional analysis. So if I have 2.1 moles, all right, it said moles. Everything happens in stoichiometry in moles. So do I need to convert to anything? No. All right. 2.1 moles of carbon dioxide that will be produced. How many moles of, of carbon dioxide? If 2.1 moles of C3H8 propane are burned in excess of oxygen. In other words, I got more oxygen than I need. So all we have to do is do our mole ratio. A lot of you are asking, how do I put this ratio down? So I'm going to put moles of C3H8 on bottom for a reason. All right, if you look at, we didn't balance the reaction, did we? Let's do that real quick. We've got to have a balanced reaction. You see I have 1 carbon on that side. I got 3 carbons on that side. So let's go ahead and put 3 carbons here. So I got 3 carbons on this side, 3 carbons on that side. Let's look at our oxygen. I got 4 hydrogens over here. I got 8 hydrogens over here. Let's put 4. Oh. Okay, so that means I got 3 carbons, that's good. I got 8 hydrogens, that's good. Now let's look at our oxygen. So oxygen, I got 4 oxygens here. I've got 6 hydrogens here. So that means I need 10 oxygens on this side, put a 5 there. That's balanced. So now let's look at our molar ratio. For every 1 mole of C3H8, all right, how many moles of carbon dioxide are produced? I put that in the numerator. Why? Because, and that was 3, because I can cancel out those moles of C3H8 using my units, right? So if I multiply that 2.1 times 3, all right, I'm going to get 6.3 moles of CO2. Problem solved. That's a pretty easy one. Man, that could be we could doctor this up and make it a test problem. I wonder. Okay, in another experiment, 400 grams of propane and 400 grams of oxygen are ignited and allowed to react. So this is a limiting reactant problem. And I want to do it the Bca method, okay? We're going to do the Bca method, and I think that's going to... and then we can also do it by dimensional analysis at a later date if you want. So first of all, before we do BCA, we have to put things into moles, right? So it says I have 400 grams, okay, of what? 400 grams of propane, C3H8. All right, and I need to multiply that by the molar mass, 1 mole C3H8. All right, divided by the molar mass of C3H8. Is that correct? 436. Yeah, it's 44.0962 grams. Not very heavy gas. So that's going to give me 9.1 moles. 9.1 moles of C3H8. That right is atrocious. You guys know that. So let's do how many moles of oxygen I've got. 400 grams of O2. All right, times the molar mass, 1 mole O2. All right, equals 32 grams of O2. That's going to give me 12.5 moles O2. O2. So let's set our reaction up and do our Bca table. Okay, I'm going to extend that out and do it on this piece of paper here, just so we have plenty of room. All right, so I've got C3, okay, H8 reacts with O2, all right, and that's going to yield carbon dioxide and water. Let's draw our table out. B, to our columns. So before, change, and after. All right. So we're going to put what we've got in there, and then we're going to reason through it. So before the reaction, I've got 9.1 moles of C3H8. Before the reaction, I've got 12.5 moles of oxygen. I have 0 moles of CO2, and I've got 0 moles of water because the reaction has not taken place. That's what we mean by that. Let's move this out of here. All right, so now I need to look at my mole. I need to look at my equation. This was my blotter pad, but I'll fold that up. All right, so we can see everything. I need to look at my reaction. I've got to reason a little bit. All right, so, all right, let's see which one's going to be limiting, and it's going to tell us right now. So for every, let's put our 5 right there, put our 3 right there, and let's put our 4 right there, because that's our balanced reaction. So for every mole of C3H8, I have 5 moles of oxygen. 1 to 5, right? 1 to 5, 1 to 5. So if that was the limiting reaction, so if I have 1, I've got, for every mole, I've got 5 moles of oxygen. So that means I would have to have 45 moles here. I don't. All right, so let's look at this one. For every 12.5 moles of oxygen, I have 1/5 moles of C3H8. So I take my 5 moles there and put it over the 1. All right, so let's look. 1/5 of 12.5 is 2.5. Do I have 2.5 moles? Yes, I've got a little over than that, right? Okay, I've got like 6.6 moles over that. I've got 9.1 moles. So that means the limiting reactant is going to be oxygen. So we're going to write O2 down there. That's it. Okay, so we're going to calculate the maximum mass of water that can be produced in this reaction. Let's go ahead and fill out our Bca table. During the change, we're going to use 12.5 moles of oxygen. All right. We're going to add 3/5 moles. Okay, for every oxygen mole, I produce 3/5 moles of CO2. So I don't have 1 mole of oxygen. I got 12.5. So 3/5 of 12.5, which is what I started with, is 7.5 moles. All right. So for every mole of oxygen, if that's all I had was 1 mole, I'm going to produce 4/5 mole of water. 4/5 of 12.5 is 10 moles. So for every mole of oxygen, I'm going to produce 1/5 mole of propane. So I don't have 1 mole of oxygen. I have 12.5 moles of oxygen. So I'm going to take 1/5 of 12.5, and that's going to give me 2.5. So I'm going to use that up. I'm adding 7.5 of carbon dioxide. I'm adding 10 moles of water. Now I just do my math. So I'm going to have 0 moles of oxygen left over. I'm going to have 6.6 moles of propane left over. And then I'm going to have 7.5 moles of carbon dioxide. I'm going to have 10 moles of water. My problem's almost solved. So let's look down here. So oxygen is the limiting reactant. Calculate the maximum mass of water that can produce in this reaction. So with what the data I have, all right, the data I have, I can only produce 10 moles, all right, 10 moles. But I have 400 grams of oxygen, all right? So I can only produce 10 moles. So what I'm going to do is figure out how many I'm going to produce 10 moles of, it's going to produce 10 moles. So I've got 10 moles of water because of the Bca table. We had 12.5 moles of oxygen. So if we used all that, we're going to produce 10 moles of water. So H2O times the molar mass of water, 18.0158 grams, over 1 mole, because that means for every 1 mole of water, it has a mass of 18.0158. And that's going to equal 180.15 grams of water. Now I'm going to do this dimensionally by dimensional analysis. So it told me, and again we know that oxygen is limiting, so I've got 400 grams of O2. All right, I've got to convert that, all right, into moles, always 32 grams of oxygen. That's the molar mass. Now I'm going to use my mole ratio. 4 moles water for 5 moles O2. And I can cancel out those units, cancel out that unit. So now I'm going to multiply that, like I did here, by 18.015 grams over 1 mole water. Cancel out. And I get, guess what? 180 grams. They both work. Use whichever method you want. But if you're going to do that question to find the limiting reactant, okay, you have to do the